In a previous couple of videos, I discussed my desire to better understand the transformer model from the Google paper Attention is All You Need. And in order to better understand this model, I took out the attention equation, the vanilla attention equation from that paper, and tried applying it to time series forecasting problems. And so I was pleasantly surprised with the performance of just this simple component out of the whole model on time series forecasting, but I also wanted to expand this and try using a full transformer encoder for the same problems so that I can compare the performance between the two. And so on this slide, I show the very small component that I used previously, and on this next slide, I show the components that I want to use. And so in order to do this, I took the transformer encoder layer class from the PyTorch library, and I combine it with a few other components. The first being a linear layer so that I can embed the inputs and perform that input embedding step, as well as PyTorch's positional encoding class so that the position of each element of our time series is encoded properly. And then in the previous video, I used a custom masking function to mask the data. And in this video, I'll show how I used the official PyTorch masking function to perform masking. And so I wanted to combine these components so that I could use a full transformer encoder for this time series forecasting problem. And on the next couple slides, I'll explain in a little more detail how each component is implemented. So the first component I want to talk about in more detail is the input embedding step. And I had a lot of trouble understanding this because when you're processing text data, you normally tokenize it as integer values and then embed those integer tokens. And so a lot of the tutorials and literature on embedding is from an integer sequence perspective. So I was very lost when it came to embedding a time series until I found this GitHub repository that's at the bottom of the slide that I'll also link in the description that did it in a very simple way that worked brilliantly, which was just to use a linear neural network layer like was done for the queries, keys, and values for the attention approach. And so how this is used is our original data matrix has a batch size dimension for the observations and a sequence length dimension for the length of the time series components that are inputs to the model. And if we append a dimension of 1 to this using PyTorch reshape, we can perform this linear approach on every element of every sequence, and it'll embed those elements as vectors just like it would for a text processing problem. And these embeddings are learned throughout the entire training of the model. And so this outputs now a data matrix that has the batch size dimension, a sequence length dimension, and an embedding size dimension. And so this becomes a lot closer to what you'd expect from a normal natural language processing problem. So after performing the embedding step, we can then pass this to the PyTorch positional encoding class. And I won't speak too much to the details of how this is implemented because they implemented exactly what's in the Attention is All You Need paper, and I just imported their implementation. But I think it's important to mention that the dimensions of our data are preserved throughout this operation. And so as we perform the positional encoding, the data is transformed so that positional information is now visible to the model, or more obvious to the model, but the dimensions of the data coming out of this step are still batch size, sequence length of the time series, and our user-defined embedding size. So having pre-processed the data with the input embedding and positional encoding steps, the data is ready to be passed to the transformer encoder layer. And as programmed in PyTorch, this component has a variety of hyperparameters. For my implementation, I only defined 4 of these. The first is the demodel parameter, which I believe is required and should be set equal to our input embedding size. But the next is the number of heads in the multi-head attention step, which controls the size of our multi-head attention. The dim feed forward parameter controls the size of our feed forward component in the transformer encoder layer. And then the dropout is just standard neural network dropout, which I'll speak a lot more to later on. And so, just like our positional encoding step, something that's interesting and important to note is that the dimensions of our data are preserved throughout the transformer encoder layer processing. And so the data coming out of this step is still of dimensions batch size, sequence length of the time series, and user-defined embedding size. So having applied the transformer encoder layer to our data, we now have this data matrix that is batch size by sequence length by embedding size. And we need to perform regression on this matrix, but for each observation we have two-dimensional data. And so this could be passed through some sort of convolutional layer or convolutional network. And I could easily see that being a very good option. But I took a simpler approach and I just flattened those final two dimensions into a single dimension very naively. And so for the problems that I experimented with, I had a sequence length of 200 and an embedding size of 8. And so when I flatten those into one dimension, it just concatenates them into a single dimension of 1600 elements. But having combined all of those elements into a single vector, we can then pass those through a feed-forward neural network to get our final regression value. And so the lower half of this slide shows our now flattened data matrix X being passed through a neural network to achieve a Y value of 1, which is our next value, our next forecasted value in the time series. So as a final note before I show off the code, I just wanted to highlight two major hiccups I had, as well as a variety of things that helped me out a lot while trying to fit these models to the time series forecasting problem. And so my first major hiccup was I originally didn't want to use the input embedding for the reasons mentioned previously, where this is typically a text data process, and I tried to keep our embedding dimension as 1 throughout the model. This does not work. The way that the PyTorch transformers are implemented, they expect an embedding dimension, and if you set that embedding dimension to 1, they don't perform as expected. And so that's why the input embedding is absolutely necessary, even for this float valued data in the time series, so that we can have a model dimension that's greater than 1. The other major hiccup that I hit was I left dropout on for the transformer class, as well as some self-implemented dropout, and this really made it difficult to fit the model. People with a lot of machine learning experience would probably shake their heads if I told them that I left dropout on for this specific problem that caused major issues, but I wanted to highlight it because in the transformer encoder layer class, dropout by default is not set to 0. And so it helped me a ton setting dropout within that class and throughout the entire model to 0. And if anyone's struggling, I hope that highlighting this might help them as well. I listed a few other things that I tried out while struggling to get the model to fit correctly. And these all helped a little bit, but they weren't the major issues highlighted above. So using AtomW instead of Atom helped out a little bit. Using a learning rate schedule helped out a little bit. Increasing the size of the regression component and dropping batch size down to 1 all helped just a little bit with the problem. And so I just wanted to briefly discuss the code that's used to tie all these components together. I won't go through training loops or any of that code, but I'll link all that in the description of the video. In terms of just putting together the pieces already discussed, I created this forecasting model class that takes as inputs all of the hyperparameters needed for the transformer encoder layer and the other components, as well as the sequence length of the expected sequences that we'll be processing for our forecasting problem. And so after setting some of these to class level parameters, I define the transformer encoder layer as discussed. It's imported from PyTorch, and I didn't mention this in the slides, but I also set this batch first parameter to true. This is important for doing the source masking the way that I've done it. And so that's an important parameter that I just wanted to call out. If you're masking, this might help if you're running into dimension issues. From there, I define a standard ReLU activation function as well as this dropout that's not used for the reasons discussed earlier. I copied code in from a PyTorch tutorial at the top of this file that's used to define the positional encoding exactly as it's defined in the Google paper. And this takes in similar parameters to the encoder layer, but also has a max length in case you didn't know what your sequence length was, as you might not for text processing problems. But we know what our sequence length is, and so we can set max length equal to our known sequence length. From there, I defined the input embedding as discussed as a linear layer where each element will be embedded to the user-defined embedding size, each element of the time series. And then the remaining linear layers are just used for the regression portion of the problem. And so this just defines a standard feed-forward network. And so in terms of the forward pass of this model, there's a function defined at the bottom of the model that is copy and pasted from the PyTorch code used to generate the mask for the input sequences. And so I'll show that function at the end, but I call that function to create a mask, and I put it to whatever device we're using for the model, whether that's a CPU or a GPU. Then I process the data using the input embedding and position encoder components, and I pass that processed data to the transformer encoder component along with the mask generated by this function. I tacked on the reshape function directly to this transformer encoder just to show that the output is automatically being reformatted to be of dimensions batch size, and then a long dimension of the flattened sequence length and embedding dimensions. And then after that, I just pass it through the feed-forward neural network for the regression. And so the rest of this is just standard linear layer activation, and then the dropouts, which are not used. Then the final component of this class is that function copied in from the PyTorch code that generates the mask. And just like the attention model, this mask is simply a upper triangular mask that hides future values from the current step in the sequence during training. So for the final part of this video, I just wanted to highlight some of the results that came out of training the models using the transformer encoder layer. On the left-hand side, I have the previous model using just basic attention, and then on the right-hand side, I have the transformer encoder results. As mentioned previously, the sine wave data is a little bit too easy, but I like it using it as a benchmark just to make sure things are working properly. With the attention model, it was already near perfect, but we can see that the amplitudes gain error as we move further and further from the real data in our forecast. I was surprised to see that the transformer encoder model has very, very little error and picks up on the pattern almost perfectly. And so I wanted to see how far this would go. So I increased the forecasting window just to stress test how well the model can do. And yeah, it stays consistently performant very far from the last real data point, at least for this extremely, extremely simple problem. But this is really interesting to see because with the basic vanilla attention implemented by hand, we still don't even see this level of performance. And so using just a basic single encoder layer, we achieve a really, really good forecast for this easy problem. But I also wanted to try it on some real-world data that wasn't as easy to forecast from. So I applied it to the same sunspots data set that I previously used for the basic attention model. And again, I have the attention results on the left and the transformer encoder results on the right. And it's exciting to see that the error is significantly better. At least I think so for the transformer encoder model. This data is definitely a lot noisier and a lot harder to pick up on, but I was really interested to see that the period of the pattern seems to align better on the transformer encoder side, and the output from the model seems to have smoothed out a little bit. The noise doesn't seem to be having as much of an effect on our output, which is also exciting to see. And so I was really motivated by these results, and I want to keep investigating and learning more about transformers and trying out larger models. So hopefully I have time to investigate a little bit more and put together some more of these videos. But until then, I thank you very much for listening, and I hopefully have some more for you soon.